Good evening, one and all. I welcome you to the fifth live session for the NPTEL course Production Technology Theory and Practice. The tutor for this particular course is Professor Shonak Kumar Chaudhary from IIT Kanpur, and myself, Arnab. I'm being allotted the PA duty for this cycle for this particular course. I hope that you have gone through the video lectures for the last week's um, you know, curriculum and also have attempted the assignment assignment questions. So I have collected a few questions from the previous year's assignments and framed a few questions from the previous week's video lectures, and we shall be discussing that in this class today. Coming to the first question, it's based on milling operation. A slab milling operation is being performed with a milling cutter of 40 mm diameter, 2 mm depth of cut, and the feed per tooth. So it's not the feed motion of the tool alone, rather the feed which is being provided per tooth is taken as 0.2 mm. So you have to calculate the maximum chip thickness in millimeter. So it's a pretty straightforward question. You can directly apply the formula that is available and get the value. But I would rather approach it in a step-by-step manner so that the thing gets clear, and also you can attempt a more complicated question or a more conceptual question that may be framed based on this. So this is one of the teeth of the milling cutter. Like this, other teeth will also be arranged around the periphery. So I am considering one of the teeth, and this is the rotation, that is the cutting velocity rather in RPM. You have the workpiece being fed in this direction. This is the feed motion of the workpiece, VF, and this is your depth of cut, delta, and this is the tool diameter, phi. So this is a case of upmilling, because if you pay your attention at this particular point, then this is the feed motion of the tool with respect to the workpiece, or the other way around, both are correct. In this case, the tool is being just rotated and the workpiece is being fed, as a classical example of any milling operation. However, in different milling operations, you can see that the tool is also moving or being fed along with the rotational motion. So that is also possible. So this is the feed motion, and in the forward direction, you have the cutting motion. So that's why you can say that it's an upmilling operation. Had these been in the same direction, then it would be a case of downmilling, right? So you're told that the feed per tooth, that is F, is equal to 0.2 mm. So what does that essentially mean? That as the as this particular teeth that I'm considering here, it moves from this particular point to this particular point, up to which you have provided the depth of cut. Rather, up to this point where this particular teeth disengages from the workpiece. So till that point, the tool, this entire tool has propagated in the forward direction with respect to the workpiece by this much amount, say by this much distance. So this will be your new position of the tool, and this particular teeth here has propagated till here. Okay. So this is the scenario. So if you look into the workpiece, you will see that this much region of the workpiece is getting chipped away or removed, right? So you can see that the chip thickness, this is the 2D view. If you project it into the plane, that then you will get a 3D view of this operation. So it will be somewhat like this. So you can see that this much amount of material is getting removed by this much feed, that is F, that is the feed per tooth by one tooth. So you can see here that the chip thickness is varying from minimum, say that is 0, to a particular value here, that is maximum. So if you draw the chip here, it will be somewhat like this. So this will be your maximum chip thickness, T max, that you are being asked to calculate here. So here you make an assumption that this particular arc, it can be approximated as a right angle triangle. So this is the 90-degree, and this particular distance, sorry, this particular distance is nothing but the feed per tooth, F. So it can also be written as Vf by N into Z. Vf by N into Z is the feed per tooth, that is millimeter, that can be given in millimeter. So you have a formula for Tmax, which is F into root over of 2D by R. So it's, sorry, it will be delta 2 into delta by R, where delta is the depth of cut. So if you are putting in the value 0.2 into root over of 2 into 2 divided by, so see, this is the radius of the cutter and you are being provided with the diameter. So you have to be careful here. It should be 1. So this is the maximum chip thickness that you are getting here. Okay, so if you are being asked about asked to calculate the MRR for this particular question, then you would have been provided with two more details. One is the feed velocity, that is Vf. So if you had to calculate MRR, then it would have been the width of the cut, that is into the plane, this width of the milling cutter, say that is W, into the delta, which is the depth of cut, into feed velocity Vf. Okay. So you had to know Vf, and F and Vf is related in this manner. Okay. So moving on to the next question. So one thing you have to remember here, that the thickness of the chip, it is not constant in case of milling, unlike in cases of turning, where you could see that the chip thickness was constant. So this was your turning operation. So these two thicknesses, we assume that to be constant during the orthogonal machining operation or any machining operation, any turning operation. But here you can see that the chip thickness is varying. And in cases of down milling, what happens? In cases of down milling, you have your tool here. This is the workpiece. So say your workpiece is being fed in this particular direction by VF. This is the depth of cut, delta. Here, the milling cutter will engage the workpiece in this manner. So this is one of the tooth that I am showing. There will be other teeth here around the periphery of the cutter. By the time this teeth will reach this bottom position, it would have removed this much material. So here you can see that the chip thickness is varying from a maximum value to 0 in case of down milling. So how will you identify this is a case of down milling? You can see that the tooth milling cutter is rotating in this particular direction by a speed say n rpm. So this is the cutting velocity, and the feed velocity is also in the same direction. It will be less than the cutting velocity, but is also in the same direction. Say this is feed. So this is a case of down milling, and in the previous case you can see this was a case of up milling operation. Here also you can apply the same formula to calculate Tmax. However, if you go into the dynamics of the machining, then you can see that the forces, the thrust force and all will be higher in this case, because you can see that as the teeth is engaging, it is engaging at a much higher chip thickness. So the forces will vary from a maximum value to a minimum value here. While in case of up milling, it will vary from a minimum value to a maximum value. And also in case of down milling, you can see that the chattering frequency will be high, because because that every time the teeth is engaging at a higher depth of cut. Sorry, not a depth of cut, higher chip thickness. Moving on to the next topic. So this is regarding wear and friction. So during machining operation, friction is a phenomena that you can't neglect. It is always present. So you have to consider the effects that is being imposed by this friction, and one of the most prominent effects is wear. So where does the wear occur? So first of all, what is wear? Wear can be defined as the loss of material between two contacting surfaces from either of the materials. So how that may happen? It can be just the material coming off from one particular surface or both the surfaces and getting lost in the process, or it can get transferred from one surface to the other surface. So both of the situations is not desirable in this particular case. So yeah, we need to study that. So how does this friction originate? So this is your particular body, say any body which is getting rubbed or slided upon this surface here by the action of a force P. So macroscopically you can say that yes, there will be one friction force which will be dragging this body, and it will be acting along the surface of contact between the body and the and the surface on which it is being slided upon. And there will also be a finite value of this normal force, which in this case may be the weight of the body, or there can be some other force acting on the body. So in that case, the normal force will be simply the force that the body is getting acted upon. So yeah, due to this normal force, what happens? You can see that if you zoom into this particular contact zone, so this is that particular view. So no surface is plane. So it will be having some undulations in the form of asperities. So this sharp edges you can see here. They can be in micrometer to nanometer range, depending on upon the surface finish, surface quality. And when two such surfaces are sliding upon each other, then what happens? Due to the action of this normal force, a high compressive stress will generate in the local point of contact. So this is, say, one asperity, and it is, sorry, one surface, and these are the point of contacts. So at this area of contact will be very less initially due to the action of the normal force F. Compressive force will act on the surface. So N by AR. AR is the real area of contact. Real area of contact is the summation of all these small areas that will occur along the entire contact length. So you can see here, since AR is very less, so the sigma C will be very high. So due to this local build up of compressive stresses, what happens? Cold welding happens between these particular contacting points. So the material gets welded here. So once it gets welded, then to there is another force which is trying to drag it in the forward direction. So to successfully drag it in the forward direction, you need to break these welds, right? You need to break these welds to drag it in the lateral direction. So this particular resistance to this forward sliding is manifested in the form of friction. I hope you understood this. If you have any doubt, you can ask. So there are a few fundamental questions which arises out of this discussion. One is like the real area of contact, as I said, it is the normal force. So you can say that sigma, which is the compressive force, is equal to normal force divided by real area of contact. You can also say that the shear force, the shear stress that is no need the shear stress that is developing due to the applied force P, which essentially needs to be equal to the friction force to make the body, like, this is the limiting condition to make the body move forward at a constant velocity, right? In case P is greater than friction force, then the body will accelerate. But if you need to just move the body, then P should be equal to F. At a constant velocity, P should be equal to F. So we are considering that limiting condition P is equal to F. So due to this friction force, the stress, the shear stress which is being generated can be written as, sorry, F, that is the friction force, divided by the real area of contact, AR, right? So there's one fundamental question, like from here you can write AR is equal to sigma is equal to F by tau. So this sigma and tau. So like what these are the properties of which material? There are two conducting materials, 1 and 2, right? So for this, which material should you consider? I can see one student here, Rekha. Can you answer this? Like, these are the properties of which particular body? It can be like a property of body 1, or it can be a property of body 2, or a combination of both. So how will you identify sigma and tau here? Am I audible? Hello? Okay, so the answer would be like these properties are for the weaker material. Okay, so there are two materials in contact with each other. So the body will slide once you are breaking the weldments. To break the weldments, you need to overcome the shear strength of the weaker material. Okay, so that's a design perspective. So from a perspective of design, you can say that these properties are for the weaker material, weaker among the sliding surfaces. Okay, so gradually what happens? Suppose you are slowly increasing the value of the normal force N. Okay, so this is your initial scenario. So if you are increasing the value of normal force N, what happens? This apparent area of contact, sorry, this real area of contact, it tends to approach the value of the apparent area of contact, or the macroscopically whatever you are seeing now, this particular area, it approaches that area. Why? Because these asperities try to get interlocked with each other, and due to some plastic deformation, they try to attain a common interface. Okay, rather than this point contact. So you can see that the area has increased significantly from AR in the initial condition to AA, which is the apparent area in this particular condition. This is for higher values of normal force. So what change in the coefficient of friction will you notice here? So initially, the coefficient of friction can be considered to be a constant, equal to F by eta, sorry, F by N. So initially it was constant, but as soon as this, the this particular zone can be termed as the sliding zone, and this particular zone can be termed as the sticking zone. Why sticking? Because due to higher normal force, the material has tried to, you know, stick to the other material. Okay, so here you will find that some plastic deformation has occurred, and here mu is not a constant value here. Just like ideally this should happen theoretically. So your curve should look like this. Okay, so this is the hypothetical case wherein, so here what happens, here the friction force, it ideally approaches a constant value, and that value is nothing but it is tau into the area, which is the real area. Okay, or the sorry, the apparent area in this case will be equal to real area. So anyway, you can write it as tau into AA. Okay, a subscript a. So this is a constant here. Okay, however, in this case, as eta increases, f also increases, because as eta increases, this apparent area slowly increases. Sorry, the real contact area slowly increases, and as a result of which f also increases, and this happens in a proportionate manner so that mu is equal to constant. But at higher values of N, this apparent area, the real area approaches the value of apparent area, and hence the friction force gradually attains a constant value. Okay, but in this region, you can see that eta is not a constant, that is the coefficient of friction is not constant here. However, this is the hypothetical case. In actual scenario, it's quite different. You can see that higher value of loads, your friction value can shoot up further. It can increase further. Okay, like this. So this deviation from the ideal case to the real case happens mainly because of this the contact that has happened at higher values of n. The contact at this point, like many phenomena occurs. Out of them, one is the interlocking of the asperities. So as the asperities get interlocked between each other, you have to break those contacts to make the body move forward. So essentially, you need a higher force to be applied to overcome that frictional force. Okay, to break this particular asperity contacts or the interlocking asperities and enable the ball to slide forward. So that's why this in the real scenario, the coefficient of friction it increases rather than it approaching a constant. I mean, the friction force doesn't attain a constant value, rather it increases. Okay, so we have a question here related to this particular theory. What causes the upward deviation of Fn curve from the hypothetical? So this was the hypothetical case here in blue, and this is the real case. So local welding of asperities, interlocking of asperities, lubrication, all of this. So lubrication will have a tendency to reduce the coefficient of friction, right? If you are applying it efficiently, then the coefficient of friction should reduce rather than increasing. But the question asks for the upward deviation. So this is not a correct answer. So interlocking of the asperities will be the correct answer. Local welding of asperities occur in the ideal case also. So that is the basic, you know, origination of friction. This is local weldment. So that is not exactly the reason for this shift. The interlocking of the asperities is a probable reason for this. So due to friction, or to physically define the phenomenon, due to the interlocking of the asperities or due to this local weldments happening, as you are trying to slide the body by applying a force, what happens? Wear happens. So material either gets removed from either of the surfaces, or it gets transferred from one surface to the other surface. So that mainly happens by three mechanisms. One is the abrasive wear, which happens due to plowing of the weaker material by action of the hardened material. Okay. Another wear mechanism is the adhesion, which happens between two similar surfaces. Suppose you are having two similar surfaces, and you somehow ensure atomic contact between them by removing the oxide layer. You are allowing the nascent atoms to come onto the surface. So as a result of which they establish a contact between them, which is also known as adhesion. So which is also known as cold welding. So that is one mechanism, and other mechanism is due to the contact pressure. With the high contact pressure, the material is getting welded. So that is one of the mechanisms due to which wear happens. The local weldments take place here, and also interlocking is a physical phenomena. Welding is a metallurgical and somewhat chemical also. And the diffusion of atoms across a concentrated gradient between the surfaces, concentration gradient. So suppose one of the surface, this is 1 and this is 2. So one of the surface is having the atoms in a higher a particular type of atoms, a particular type of atom at a higher concentration, and the same atom is present in the other surface at a lower concentration. In that case, due to this concentration gradient and a nascent type of contact which is happening between these two surfaces under the action of this normal force, the atoms diffuse from surface 2 to surface 1 across the concentration gradient, and as a result of this, diffusion bonding takes place. The diffusion bonding is also a factor which increases the friction force, and as a result of which wear takes place. Gradual transport or loss of material from a body, that is the general definition of wear. It's not a mechanism as such, but it encapsulates all the three mechanisms. With very high normal pressure at the chip tool interface, the ratio of the real area of contact and the apparent area of contact becomes equal to 1, less than 1, more than 1 does not get affected. So as we already discussed, this was the initial case when the value of the normal force is less. You are having a very low contact area, real contact area, and this is the apparent contact area total. At higher loads, severe plastic deformation occurs, and these asperities get interlocked, and they assume a fairly like equivalent area of apparent contact. Like if this was AA, so this AR will be fairly equal to AA. Okay. So the ratio it is equal to 1 at higher value of normal force. Okay, so why we are reading this particular phenomena here? Because if we relate it to machining, during say turning operation, you have a tool which is interfacing with the workpiece with a particular depth of cut at a particular depth of cut, and in this zone a severe plastic deformation is happening, and as a result of which this material is getting separated and it is flowing on the tool in the form of a chip. Now as the material is flowing on the tool or the rake surface, to be more particular, this will be the contact length after which it separates out from the surface of the tool and it flows away. So from this point to this point, you can see the above phenomena, that is the sliding and the sticking zone, prominently taking place here. Okay, so you can divide this area into two zones. So initially the contact pressure will be very high. Here the value of normal force is very high, which slowly decreases in the upper portion. So this one will be the sticking zone, where we can say the value of mu is not constant, sorry. And this is the sliding zone, where mu is equal to constant. Okay. So the contact pressure is pretty high here. That's why we can say that it enters into the sticking zone. So the friction that we are seeing here, it is not a sliding friction, rather it is a sticking sliding friction. Okay. So that's why whenever we are drawing the merchant circle diagram, even in the last class, we have discussed that the value of the coefficient of friction which we are calculating, it is the apparent coefficient of friction, or sometimes we refer to it as the average coefficient of friction. But in actual, the real coefficient of friction, I mean real as in for the entire surface, if we actually try to calculate out, we have to integrate along this entire length. the individual forces. So the not this is the normal force here, which is acting normal to the surface, and we'll also be having a frictional force to be acting like this. Sorry, it will be rather in the opposite direction. If we are considering the force which is acting on the rake surface, then this is the direction. If we are considering the force acting on the chip, then it will be the opposite direction. So this is friction. F. So F is related to the shear properties of the material, shear stress, shear strength, and N, which is the normal force, is related to the compressive stress of the material or the compressive strength, not of the material per se, of the surface. So the surface properties may differ from the bulk properties of the material. So, if we consider the tool and we are coating it with a particular material to improve its wear characteristics, then we are improving this shear stress and the normal stress of that surface and not the bulk material. So coming to the next question, as the working normal rake angle increases, the mean normal stress will increase, will not be affected, will decrease, will be doubled. If you have gone through the video lectures carefully, then in one of them sir has already discussed the derivation for this tau and sigma, and from there we could calculate the value of coefficient of friction, which is nothing but by n, or so from here we arrived at a particular equation that so if we so lambda is your friction angle. This is the mean stress, mean normal stress, or the compressive stress here, which is acting the on the surface of the on the rake surface, and K is a constant which includes the shear portion of the shear component of the stress, and some other information like the length of contact. So all those can be fairly assumed as constant over a larger range of unlubricated conditions. So using lubrication you can reduce that. So that's why I'm saying it's unlubricated condition, and it has been seen it is constant for a given material over a large range of cutting parameters. So this is constant. So you can see that so your question asks about the normal rake angle. So as gamma n it increases, so initially your tool was like this. See, if you would have drawn your Merchant circle diagram, this is the F, this is N, say this is R. So for the given resultant, so if R would have been constant, say now this was the gamma naught, gamma n1. Now you have increased it to gamma n2. This is your new tool where you have gamma n2. So what happens? You can see that the friction force component will be like this. The normal force will decrease. Ideally, like R will also vary. However, if you are considering that to be constant, you can see that the normal forces decrease, and as a result of which you can say that the normal stresses have also reduced, right? What happens? Yeah, because n reduces. So if this happens, you can see from the angles here, this was the initial angle and now the angle has increased. So lambda increases. Increases here. Okay. So moving on to the next question. For tool crater wear, the mechanism of wear which is primarily responsible. So, there are different types of wear mechanisms which are taking place at the chip tool interface. So, one of them is a crater wear. That happens mostly because of the diffusion type of phenomena that's occurring. We have discussed different types of mechanisms: abrasion, diffusion, adhesion. This mainly occurs due to diffusion phenomena, in which some of the tool material it no diffuses into the workpiece material or the chip material due to a concentration gradient, which weakens the tool material here, and that's why when this is getting away, this thing is separating, it is taking away that small micro volume of the material which was adhered to it due to diffusion bonding. Coming to the next question of 15 mm by 15 mm square cantilever beam is subjected to a normal force of 200 Newton. The strain measured by a strain gauge at a distance 20 mm from the point of application of force. This question is related to measurement of forces. If you can simulate the any operation, say turning operation. So you have the tool here. I'm drawing a 3D view. So you have this particular portion fixed to the tool post, and this particular portion which is the free end, and you have your workpiece material which is being interfaced here. Yeah. And here the chip is flowing. Okay. So this can be considered equivalent to this particular scenario, wherein you have a fixed end and another end which is free, which is a cantilever beam. Okay. It is also provided a feed motion. So essentially will be acted, this environment can be simulated by this particular simplified diagram. So you have vertical force which is acting on the surface, and if you take a cross section of this, and you also have another force which is acting in this direction, which is the transverse force. Okay, so this was the cutting force, and another force used to be there in this direction, which is fxy. As we had seen in merchant circle diagram, we can consider it as transverse force. Okay, this is a cutting force, this is a transverse force. In this case, you are told that it is only being acted upon by a normal force, that is here we can consider it as Fc alone. This and you have a strain gauge which is placed at 20 mm from the point of application of force. So this is F. So your strain gauge is somewhere here. So as you are applying the force, this will try to expand and this will try to contact. And from there you can find out from this extent of expansion, which can be defined as strain, may be related to the force which is acting. And if you are able to calculate this particular value of strain by measuring the voltage changes, then you can fairly estimate the value of the force using some calibration principles and all. So yeah, you have a direct formula here, so you can directly apply that. It is derived from some principles of strength of material. So you can say that the strain here is equal to 6F into L divided by H square. What is F here? F is the normal force which is acting normal to this section here, Fc. L is the distance between the point of application of force here to the strain gauge. B and H are these dimensions of the cross section of the beam. Okay, I think the value of E is missing here, or you can substitute the other values. 6 into 200 into L is 20 mm. Divided by E into BH square. So it's 15 into 15 square. Okay, so yeah, you need the value of E. Suppose you have like you take a simple case of fine steel. In that case, your value of E will be around 200 GPa. So if you substitute that, you will get the value of strain. Okay. Generally, will be provided with the value of E. Uh, I think I have not written it correctly from the question. So yeah, you will be provided with the value of E. In Taylor's tool life equation, Vt power n equal to C, which is the Taylor's tool life equation. C is the intercept on the speed axis, the slope of the plot, the cutting speed for 1 minute of tool life. Intercept on the tool life axis, constant, tool life for a unit cutting velocity. So we know that if P is equal to 1, that is, or you can also say that for 1 minute of cutting tool life, the speed is equal to this constant. Okay. Vt power n equal to constant. So 1 minute, this minute unit should be kept in mind. So the cutting speed for 1 unit of tool life, so 5/5 one is a correct option. You can also say, like, if you take a logarithmic plot of this, log v plus n log t is log c, which you can consider as another constant k. This say is your x, this is your y, so it is y equal to mx plus c. This is generally minus mx here, because it's, if you take it to the right hand side, then this will happen. N is your slope of the plot here, right? Minus n. and this will be the actual relationship here. So here it should be logarithmic scales, not normal linear scales. So the slope is defined by n, and k is the intercept. So if you put log t is equal to 0, then k is log v, right? So at log t equal to 0, so this y intercept is nothing but your c here, or sorry, it is k. C is, how will you calculate c? Basically log c is equal to k, 10 power k. So this is denoted by, like here we are taking as logarithmic scales, but like in the question it hasn't been mentioned, like the speed axis, this tool life axis, it hasn't been mentioned that they are logarithmic, but you can assume them to be on logarithmic scales, and you can write that it is the intercept on the cutting velocity axis, right? On the speed axis, the intercept. So 1 and 5, which option is having 1 and 5? There are two options which is having 1 and 5. So slope of the plot is not the correct option. 4, it is a constant. Yeah, it is always, it is a material constant. So 1, 4 and 5 is the correct option here. In a turning operation using a high speed steel tool, the cutting velocity v is equal to 90 meter per minute is used. The Taylor's tool life equation has parameters n is equal to 0.12, c is equal to 130 meter per minute. So you can see that this unit and this unit are same. When the operation is conducted dry, when a coolant is used in the operation with the same cutting speed, the value of c is increased by 10%. The percentage increase in tool life is, so this is the dry condition. Using a coolant, c increases by 10%. So it becomes 1.1 into 130, right? If it increases by 10%, the new c is, so I am denoting it as v1. N will be constant in both the cases. So c2 is 1.1 into 130, 43 meter per minute. So you can apply Taylor's tool life equation here. Vt power n equal to constant. Okay, you are told that v1 and v2 are same here. Okay, so initially you have to calculate the value of T1. So from here you can see 90 into T1 power 0.12 is equal to 130. 130 by 90. This is T1. Now coming to T2. So V2 is same, here V2 T2 or n is equal to C2. So n is also being assumed to be constant here. On 43. So you can see a significant increase in the cutting tool life. So you have been asked to calculate the percentage increase in tool life. So it increases by more than 100%. See, just by putting some suitable coolant environment or lubrication environment. So what happens? This from here you can see that what this C depends upon. So C is it is generally a constant. It is considered a constant. This N and C. So what parameters do they depend upon? It depends on the material. This N depends on the material. The C depends on the cutting conditions. Like here you can see in dry condition the value of C is less, and in like under lubricated conditions or under the application of coolants it's higher. So accordingly the life of the tool is also increasing. So that's it for today's class. If you are having any other doubts related to this class or previous sessions, you can come up and in the next class, or you can also submit them on the NPTEL portal. Okay, thank you.